Okay, so now that we've talked about limits, we know how to look at a graph to figure out our limits. We can use a table to figure it out. Now we're going to start using some analytic methods to understand and calculate our limits. So from last time, we know that the limit of a function, especially a linear function, of f of x, the limit as x approaches a, will equal the value of the function at that point because it is a linear line. It's continuous, and it's going to be the same from the left and the right. So this is only true on a linear function, right? If some x gives me some f of a value, as I approach from the left, as I approach from the right, I'm getting the value f of a. So for linear functions, the limit of x of a, as x approaches a of f of x, is always going to equal f of a, whatever that function value is. The bigger problem comes when we don't have just linear functions. So we're going to use some rules here to work with these limits. So we're going to assume that the limit as x approaches a of f of x and the limit of f of g of x as x approaches a are going to exist. So this property holds as long as c is a real number, m is greater than 0, and n greater than 0 are both integers. So basically what this is saying is if I'm taking the sum of two functions and trying to find their limit, I can break them apart into the sum of the individual limits. Same thing for a difference. For a constant multiple, if I'm multiplying a function by some constant and taking the limit, I'm allowed to move the constant out front. If I'm taking the limit of a product, I can take the limit of each of the factors of that product. Similar for a quotient, I can take the limit of each piece of my function. For a power, I can take the limit of the function raised to the power, or I can just take the limit of the function and then raise it to that exponent. And the same thing works with a fractional exponent. Okay, so our limit laws make a little bit more sense when we actually kind of see them in motion. So this says find the limit as x approaches 3 of x squared minus 4 over x minus 2 using our limit laws. So I would use, since this is a quotient, I would say this is the same as saying the limit as x approaches 3 of x squared minus 4 divided by the limit as x approaches 3 of x minus 2. Okay. And then we know our limit laws. We could take a look at this. X squared minus 4 is a completely defined function, so my limit as x approaches 3 is just going to be the value of the function. So 3 squared is 9, 9 minus 4 is 5. Limit of x approaches 3 of x minus 2 is a linear function, so we know it's just equal to the value of f of a, so of f of x in this case. So 3 minus 2 is equal to 1. So this limit is just equal to 5. And again, here I just have it written out so you can see exactly what we're doing. In this one, I broke it down even a little bit further and broke apart the difference of function into two separate functions. Now, you don't always have to go through all of those. Sometimes we can do what we call direct substitution. But before we get to direct substitution, we're going to keep practice using our limit laws. So find the limit as x approaches 4 of square root of x. So remember, the square root is just an exponent. So really, we can rewrite this as the limit as x approaches 4 of x, and then raise that to the 1/2 power. So the limit as x approaches 4 of x is just 4, and then I raise that to the 1/2 power. And so this limit is equal to 2. And again, here just rewrote it so we could kind of see it. We took the radical onto the outside. Okay, similar type of problem, except this time we're finding the limit as x approaches -1 of the square root of x. So again, I'm going to move that radical out and take the limit of just the function as x approaches -1 of x. So that limit would be -1, so I get the square root of -1, but this doesn't exist. Right? When we're dealing with calculus, we're dealing with a real number plane. We said for our limit laws, they have to be real numbers. The square root of -1 is what we call I. It's an imaginary number. We've seen it before, but we can't take that limit. And again, we can see here, it can't be done. Okay, so when we want to evaluate our limits, we have a few options. The first thing, which we've kind of done here, but we used our limit laws just to see how they worked and broke things down, is direct substitution. If I can just plug in the value of x and evaluate the function and it works, fantastic. But sometimes that doesn't work. It will end up with a 0 in the denominator or something that's undefined that we just can't work with. So that's when we're going to turn to either a simplification, which means we probably had a rational expression, or rationalization, which means we probably had a radical somewhere in the denominator. All right, so we want to evaluate the limit as x approaches 2 of x squared plus 4x minus 12 over x squared minus 2x. Well, if I just plug 2 straight in, I'm going to get 0 divided by 0. That doesn't work. I can't do it. So what I can do first is try to simplify. So I'm going to look at x squared plus 4x minus 12 over x squared minus 2x. Now right here I'm just doing work. I'm not evaluating a limit, so I didn't keep writing limit. If we were actually still working on the limit right now, you would have to have that limit written out front. You can't just stop writing it and add it in when you feel like it. So right now I'm only focusing on this slide. So I'm going to factor x squared plus 4x minus 12, so that's x plus 6 and x minus 2. My denominator factors to x times x minus 2. My x minus 2's simplify. So now what I can do is I can say, okay, since it simplified to x plus 6 over 6, let's take the limit as x approaches 2 of x plus 6 divided by x. Okay, so here I have it rewritten. So here I did my simplification in the problem and I left the limit written there and we got down to here. So we're equaling the limit as x approaches 2 of x plus 6 over x. I use direct substitution. I'm plugging the 2's in where I see that. So I have the limit as x approaches 2 of 8 divided by 2. And so x just equals 4. All right, so here's another one involving a radical. So I have the limit as t approaches 4 of t minus the square root of 3t plus 4 all over 4 minus t. Again, if I plug 4 in for the t, I'm going to get a 0 in the denominator. It's not going to work. I can't factor anything here, so factoring is no longer an option. So when that happens and I see a radical, the trick is to get rid of the radical where it is. So usually when we have radicals in denominators, we call it rationalizing the denominator. Since this time the radical's in the numerator, I want to rationalize the numerator, and remember we do that by multiplying by the conjugate. So here I'm showing all of my work. Notice I have to write the word limit each time. I didn't go off to the side and write work, but we could have. I could have said, okay, work, and just worked here, and said t minus the square root of 3t plus 4. And then the conjugate means switch the sign, so t plus the square root of 3t plus 4. Remember, only the sign in between switches. Whatever I do to the numerator, I have to do to the denominator, so I'm multiplying by t plus the square root of 3t minus 4. And this is where that algebra comes in, right? This part of the problem, there's no calculus involved. We're just doing algebra work. So I have that figured out over here. Right here, I've already typed it in. I've multiplied it out. And then I simplify my numerator, and I get down to the limit as t approaches 4 of t squared minus 3t minus 4 all over 4 minus t times t plus the square root of 3t plus 4. Okay, my numerator, t squared minus 3t minus 4, I can keep factoring, so that's t minus 4, t plus 1. And then right here, the t minus 4 and the 4 minus t, those continue to simplify. These are opposite factors, so these simplified to give me this negative 1 right here. So now I'm just substituting because I'm not going to get a 0 in my denominator here if I plug in a 4. Once I plug in that 4, I don't have to write the word limit anymore, and I simplify and I get negative 5/8. Now just in case we wanted to see that actual substitution, I did negative 4 plus 1 all over 4 plus the square root of 12 plus 4. So I had negative 5 over 4 plus the square root of 16, which is where I got my negative 5/8. Okay. The last thing we want to talk about in evaluating our limits using our limit laws is what we call the squeeze theorem. And so this says if we have 3 functions, f, g, and h, and I know that the value of f of x is always less than or equal to the value of g of x, which is always less than or equal to the value of h of x for any value of x near a particular point, so not the entire graph, just at a specific spot, except maybe that exact value, that we can say that those limits, if the limit as x approaches a of f of x is the same as the limit as x approaches a of h of x, and those two are the same and they both equal the same number L, the limit of that middle function, it's getting squeezed in between them, has to also equal L. So here on this picture, this pink graph is my h of x graph, the blue graph is my f of x graph, and g of x is this black curve in between. And as x is approaching a, notice the limit of h of x as x approaches a is L, the limit of f of x as x approaches a is L, which means g of x has to be in between them. So here I can see that that's the limit, but sometimes when we're working with functions and we're trying to evaluate the limit, we're going to have to use that squeeze theorem to actually figure out what that point is. All right, so we want to evaluate the limit as x approaches 0 of x squared times the cosine of 1 over x. Well, I can't plug 0 in because I'd have an undefined function angle. I can't do it. So what we notice instead is we said, okay, we know that negative 1 is always less than or equal to cosine of x, which is always less than or equal to 1. Okay, well, we don't just have the cosine x. So as long as we don't go near x equals 0, we would also be able to say that negative 1 is less than or equal to cosine of 1 over x, which is less than 1, right? We're still saying the same thing. The cosine of any angle has to be between negative 1 and 1. We just redefined our angle. Okay, well, we want x squared. So since I took this inequality, as long as I do the same thing to all parts of the inequality, it's safe. So I'm going to multiply everything by x squared. I know x squared is a positive number, so none of my signs are going to change. So I get that negative x is less than or equal to x squared, the cosine of 1 over x, which is less than or equal to x squared. All right, so using my squeeze theorem, negative x squared, we know is an upside down parabola, and it hits 0, 0. I know that positive x squared is a right side up parabola that also hits 0, 0. And so now we have this graph x squared cosine 1 of x that has to always be between them, and we're looking specifically at 0, and since these have the same limit, this is telling me that this limit is getting squeezed in between and it has to equal 0. All right, so again, saying that we know the limit as x approaches 0 of x squared, that had to equal 0. The limit as x approaches 0 of negative x squared had to equal 0. So this guy had to be squeezed in between. It has to equal 0. Now, I sketched the x squared graph. I sketched the negative x squared graph. This green graph here is what x squared cosine 1 over x actually looks like. And the whole thing is always squeezed between them. And this is how we found what happened right where we know it's undefined.